week 5. Hope you're all doing well. And we've had a few people with some great questions and comments that are helping us tweak and tune our training material. So just a couple of brief updates. Be sure to check that the Zoom name you're using is the same or similar to what you use for registration, so we can track participation. That's important for us, and just making sure everybody's attending and participating, and that we know who's participating in the Zoom meetings. A few announcements, I made them before, but the GPU hackathon, there should be an SDSC GPU hackathon, is in May, and we're encouraging people to put together teams. If you have some research project that is already on GPU and you'd like to optimize it for the V100 architecture, or if you have some CPU code that you want to migrate to the GPU V100 architecture, or you have some other code that you want to look at, this the hackathons are hosted and funded by NVIDIA. And they run about a week, and they're not full long days as we know it, like 4 to 6 hours. But you put together a small team of 6 to 8 people, and then you'll have mentors. Each of the teams has a couple of mentors, and they help optimize your code. And for example, significant papers come out of this for the participants. And so it's a really unique experience. There's one at SDSC, but if you go to their hackathon page, which you can get to from our link, you'll see there's hackathons being held all year long. So let's say the May timeline doesn't work for you, you can apply to any of the hackathons, and they're hosted all over the US, and they have different focuses. Ours is data science and machine learning, but that doesn't mean you can't do something else. It is competitive, but that's pretty good, results can come out of, you have a good shot at being picked. And then associated with that is something new that NVIDIA is putting together is we need mentors to mentor the teams. And a reward would be, for example, you might be a co-author on a paper that comes out of it, or you just get the joy of learning and you become more of an expert than you thought possible. But now they've got a new program, an NVIDIA mentor program that comes with certificates and certification and badges, basically. So you go through some online training, and anybody can do it, undergraduates, graduates, professionals, researchers, and you can become a certified mentor and put that in your resume, but also that makes you eligible to help mentor at these hackathons. So it's quite fun. And I encourage you guys to look at that no matter what your level of education and experiences are. Even undergraduates who haven't had a lot of GPU, if you can get through the training gate that they've set up, they have classes that you have to take and training material. If you pass through it, then you can be a mentor. So it's really a fun way to get more engaged with an important technology. And then we have a couple of openings for research experience undergraduates. These are called REUs. And it's going to shut down soon because we need to pick some people, but take a look at it. There are some, unlike other research internships at SDSC, these do have a US citizenship requirement, but we will be having other openings as well. So check out the handshake link to that. And next today, let's see if I can get back here. Change my slide. Today's topic is we're moving into CPU computing, starting with OpenMP, and next week we'll do MPI, and then we'll get into some performance monitoring and stuff like that. So this is the repo. Mahidar is talking about that today. And I've uploaded some instructions to help you report your work by setting up the directories and getting the right permissions. We're all in the same group, so we need to have group access. And so there is a trust factor here, but since this is an open group of people, we're all working together, I'm not too worried about that. But what I need is this, you have to set the group access so I can at least read and execute and CD into your directories. So those instructions are in there. And so try to make sure you've done that recursively for all the files you've put into your practice folder. And this is just so I can go, yeah, student XYZ did do the work and it got most of it done, so it's pretty good. And so you get some credit, and that contributes to the CCR or the certification. And then the Jupyter Notebook, there was some trouble with that, and we've got that resolved. It was really a file permission for a central Anaconda installation, which gets you Jupyter and all Jupyter Lab, Jupyter Notebook, and you would need that for running the Jupyter Notebooks that are in the homeworks. So we think we have fixed that, but please post to the group or post to me, and we'll try to solve other technologies. So with that, I'll stop. Anybody have any questions about that, or any other questions you want to ask about regarding the class or what we've done to date? All right, then Mahi, you can share. I'll let you take over, and we'll see you guys on the other side.
Thanks, Mary. Let me get my video on and screen share. Right. Excuse me. So you can all see the first slide, right?
Yes, I can see it, and I can hear you.
All right, thank you. So basically, we'll have two lectures like this week and next week, looking at parallelization. And today we'll do OpenMP, and next week we'll be doing MPI. And some of the examples I'm doing today, you could rewrite using MPI to kind of see the comparison. But so let's get started. So before I get into the details of OpenMP, just wanted to go over like why you might need an approach like this, or the typical parallelization approaches that you need. So like most supercomputer architectures right now are multi-socket server nodes. So you have non-uniformity in the memory access. So I think on the right down here, this might be, I think that's Xeon Phi architecture. But anyway, right now, if you look at the AMD ROM architecture, you have on each, so you have two sockets on Expanse, and basically each socket has 64 cores, and the 64 cores are actually laid out in 8 chiplets. So you kind of have varying memory access distances essentially. So there's always a non-uniformity in the memory access on a single node itself. And then we have, of course, have a bunch of accelerators like GPUs, for example, that add on to the resources that you have on a node. And you take a node like this, and if you look at Expanse, you have 128 cores. So there's a lot of power in a single node. And then you parallelize across a bunch of nodes using a high-performance interconnect. So it could be InfiniBand, for example, which is what we have on Expanse. So to get good performance out of it, you need some kind of scalable parallel programming approach. So let me go to the next slide. And if you look at the network topologies, they can be complex also. You can have a mesh topology, you could have a torus topology. We had a machine at SDSC a few years ago called Gordon, which had this topology of a 3D torus, and that yellow box actually is a switch with 16 nodes. So you had basically a 4 by 4 by 4 torus with 16 nodes at each of the nodes of the torus, and you ended up with 1024 nodes, but in a torus configuration. Expanse is more of a hybrid factory approach. So you'll see within a rack we have full connectivity, and then between racks we have a little bit of oversubscription. And then there are other network options that are available. So this is more relevant to the MPI aspect that Mary will talk about next week, but just wanted to give an overview of how the systems look. Uh, so parallel computing, you're essentially executing instructions concurrently on physical resources. So it's not time slicing, you're taking a problem, breaking it up into pieces, and then different cores are running different pieces at the same time. And then you need some kind of synchronization as you go along, evolving in time. So the benefit of that is obvious. You get larger capacity. So you have an aggregate memory that's much larger than a single node kind of situation. And then, of course, you get the scaling and performance and being able to get to some meaningful solution in a reasonable time period. Now, that looks all great, but then there's cost and complexity to doing this kind of thing. Basically coordinating tasks and resources and also being efficient with the like you don't want to end up with a situation where you've broken up your problem into too many small pieces and you're spending more time communicating between these tasks rather than actually running the compute on the task. So there's a efficiency paradigm there. And there are several different approaches you can do for parallelism, and that involves basically memory, communication, and execution aspects. So shared memory, the communication model is using the memory on the single node. This is what we'll do today, looking at OpenMP. There's the distributed model where you can exchange messages explicitly between the tasks, and the memory associated with each task is kind of isolated from the other. And of course, this also means that you could have those tasks sitting on different nodes. So that's kind of the memory and communication aspect. Now, I said shared and distributed, but then most codes now have a hybrid model, which is basically you might be doing a few MPI tasks on each node, and then each of those MPI tasks is spawning threads. So that's the hybrid model that I didn't mention here, but that's basically what happens now. In terms of execution models, again, you can have different kinds of approaches. So OpenMP does what is called a fork join approach, and I'll talk about that in the next slide, I think. And then, but you could also do the MPI message passing kind of approach where the tasks are completely separate, and then you're communicating them between them explicitly. So what is OpenMP? It's basically high-level parallelism extraction based on threads. It's very easy to use. It's really suitable for an incremental approach, which means like if you have a serial code, you don't have to change the entire code at the same time. Like with MPI, you essentially have to write like a model that is distributed for the whole code. It's not feasible to change small pieces of it. But with OpenMP, you could do an incremental approach. You can say, oh, this is the routine that's taking most of the time. I'll parallelize that using threads on a single node. And this is a evolving standard, and I think I have a link at the end with the specifications part of it. All compilers supported, NUMA, Intel, PGI, etc. They all have flags to enable processing of these things. And how is OpenMP dealing with the parallelism? Basically, what you do is you have compiler directives and you have some library routines, and then you can guide the number of threads and other kind of aspects of how things execute using some environmental variables. C, C++, Fortran all have these directive options. So the OpenMP model, as I mentioned, is a fork join kind of execution. So the process starts single threaded. So there's a master thread. and it forks child threads in parallel regions. And then you can synchronize and disband the threads. You can, and if you're doing this a lot, you can mitigate the overhead by reusing threads. But the master thread continues all the execution of the serial phases. So the work decomposition you do using programming constructs, and I'll give you some examples. And then you can lay out the scope, and you can also lay out like the memory aspects of it. And the mapping to the threads that you're using can be static or dynamic, which means you can either say, I have a fixed number of threads and you just break it down, or you can say that I'm going to change the number of threads, or the workload assigned to a thread can be dynamically changed based on some environmental variables. And barriers and synchronizations are automatically in place, but you can also specify things like not waiting on, explicitly say that don't wait on something and then synchronize manually later, but you have those options. So as I mentioned, the main way of doing the parallelism is using compiler directives. So the functionality you can enable is basically spawn a parallel region, divide the code among threads. You can distribute the loop iterations over threads. You can also control like serialization of parts of the code, and I'll talk about some of these examples later. And you can do synchronization. So there's an example down there, which is basically how you would do a directive. So you can say it's pragma OpenMP, OMP, parallel, and you can say default all my variables are shared. So all the memory, all the variables are visible to all the threads. But then you can also say that, hey, I want these two variables to be private. That is, each thread will have its own copy of these two variables. And you would need that to kind of set up some of the parallelism. So that's kind of the example of a parallel region construct. You can say, okay, do a parallel thing. You can have a clause of like how, and like a logical expression, for example. Give it a bunch of info on like the type, the memory handling for the variables, and then you can also do reduction operations, which is an option. And you can set number of threads if you want, or you can do that at the environmental variable level. And then you can have the end of the construct at the end. So you can have some code based on all this, and then you can have an end parallel. So I mentioned the data aspect of it, so let's look at that first. So there are several data scope attribution clauses. So when you say private, the variables in that list are private to each thread. When you say shared, they're shared among all threads. If you set something as a default scope, then that will apply to all the variables unless you explicitly specify otherwise. And then you saw something called first private, which is basically the variables are private, and you initialized according to the value that is there prior to entry into the parallel or the work sharing construct. So you may have initialized something in the main master thread, for example, and then that gets pulled into the parallel or work sharing construct. And then the last private is basically you take the value from the last iteration or section and then copy it back to the original. So there are all these options. There are, and I have a link at the end which has a link to a very detailed tutorial at Livermore, which has really nice examples of all these things. It's probably too long for doing it today. But the other thing you can do is reduction operations, like I mentioned. So that will be the reduction on the variables. So let's jump in and look at a simple C example. So you're including omp.h. and then you're saying in the main function, basically you have the number of threads and the thread ID defined as a variable. And then you're saying the thread ID is private, which is logical, right? You don't want the thread ID to be overwritten by something else. So in this case, basically we're setting the parallel section with basically a private thread ID variable. And there is this function, remember I mentioned the libraries. So this is one of the examples. So you have an OMP get thread num, which will tell you which thread number it is. And this is useful in basically figuring out how you want to parallelize your particular problem. And then the number of threads, there is a different function that you can find out based on. And here we are saying, hey, we're going to just run this on master because we don't want all of them writing to the same variable, all the threads. So you're just saying this particular piece will run on master. So this is the serialized part that I was talking about. And then you just output this info from all the threads. And we'll look at the output of sample output of this thing. So equivalent Fortran program, again, we are basically setting, defining those variables, and then very similar thing, right? There's a parallel private thread ID piece, and then there's the number of threads piece, and then we're writing it out. So looks very similar. And all you're doing here is essentially adding these directives to an existing serial code, and you're now able to, break things up. Like here, we are doing a very simple thing and finding the ID, but you could be doing different work based on the ID. So compiling, and I'll run through these in the slides first, and we can do all the examples at the end. Actually, maybe not. I should probably just do the example. Let me do that. So, compiling on Expanse or any other machine, essentially you need a compiler. So I'm going to load the GCC compiler, and essentially this -f OpenMP flag is all you need to tell the compiler that, hey, I got some OpenMP code here. And that's it. With the Fortran and GCC both have the same flag. And let me see. Okay, let me show you the job script, and then we can jump into the into the scripts. All these examples are in the repo. So if you do a pull to get the latest week 5 stuff, you'll have all the example files. So the job script. Now, one thing is on Expanse, we have quite a lot of cores per node. We have 128. So we want to make sure we use the shared partition, because all these examples are quite quick and small things, and you don't want to waste 128 cores on it. So we have a shared partition here, nodes equals 1 and task per node equals 8. And then we are saying the account that we're going to use, you need to change this. I have XYZ123, you need to change it to your allocation. And so we are saying modulo.gcc, so that we have the consistent environment there. And then we are saying OMP num threads equals 8. So this is saying we're going to do 8 tasks. Now, if you don't specify this, and you can run this experiment yourself, most likely what's going to happen is you're going to pick up the end task. Actually, this is probably, I should probably change this. Anyway, to be strict, I should change this to end task per node equals 1, and then CPUs per task equals 8. But anyway, it'll probably pick that up if you do that. So, but let's be explicit and say OMP num threads equals 8. So I'm going to modify the example to change that, so that we are strictly consistent with the scheduler also. So yeah, you have, and then once you set the number of threads, all you do is run the executable. So we are running the hello Fortran and hello C. So let me hop over and share the terminal. I think it's this one. So can everyone see my terminal now?
Yes, and
Okay.
the font size looks good.
Font size is good. Okay, thanks. I can maybe bump it up one more, couple of more without, oops. Yeah. So you'll see all the examples here, and so I'm going to say, we can do that experiment. So let me do this. So I'm going to change this to 1 here and do SPatch CPUs per task equals 8.
Mahi, are you typing? Because I'm not seeing any typing in the terminal window.
Oh, did we lose the?
Something's not refreshing. So I think you need to make a new window. New share.
Oh, it's actually, is it good now?
Yes.
Okay. Somehow it paused my sharing. That's kind of interesting. So what I changed is basically n tasks per node equals 1, and then did CPUs per task equals 8. So let's do the experiment, right? Let's run this spatch dash. Oh, first let's compile it. So hello. So I'm going to do module load GCC and GCC minus F OpenMP minus O. Oops. Hello underscore C. Right, so that compiles that, and then G Fortran, same thing, minus O hello underscore Fortran. Oh, it's just F90. Okay. All right. So we have both the, now you should see the two executables. So you can see the timestamp is 130, which is now. So we just created these two. And let's first run it with the OMP num thread set, which will obviously pick up the right number. So we have, so this U300 should change to your allocation, but anyway, that's my job. It should hopefully get through quickly. Yeah, it's gone. So let's look at the output now. And you can see, oh, I should have separated out the Fortran and C, but basically you can see both of them doing the shared memory world, thread 0 of 8, thread 1 of 8, and so on. And you notice that it's all out of order, and that's because each thread is going to write, and it can be out of sequence. I think there is actually a clause that you can use to make it do it in sequence, but you don't want to be doing that. So let's change this now and say, hey, I'm going to just not specify this. And let's see if it picks up the 8 threads, or if it. So there are two possibilities, right? It's going to pick up look at the scheduler and pick up the 8 threads. And or you would end up with 128 threads, because it looks at the compute node and says, hey, you have 128 cores, so I'm going to use all of them. So let's see what happens. Typically, it's supposed to follow the scheduler, but never know. And in general, it's best to be careful. And so let me just make sure I have that. Yeah, I commented that out. Okay. So let's see. Looks like it did the right thing. So it still picks up the 8 threads. So it picked up from the scheduler. And so this is important more when you're doing hybrid cases, like when you're doing MPI and OpenMP. So, and like, let me go back to that script. So this n task per node is basically what MPI, the number of MPI tasks will end up being. So you want to make sure these combinations are right when you're doing hybrid cores, because otherwise what you're going to end up with is either like severe oversubscription because it uses all 128 cores, uh, or like if you forget to do the CPUs per task, all your OpenMP threads might end up on the one task that the MPI was binding to one core. So you want to be careful with that. But with just a pure OpenMP, it's not going to make a big difference. So that's like the simple uh, code that we looked at. Let's go back to the presentation now. And you can, I think the machine's empty enough so you can try to follow along, but you don't have to. You can try out the examples. I think it should be okay. You all should probably get through pretty quickly. So I assume you can all see the presentation again.
Yes.
Okay, thanks. So the work sharing, right? There are different ways of doing these, the work sharing. So you can do a static, so there's various options. So you can do a static work sharing where basically you say, you know, you have this many loop iterations and you're going to just statically divide them. And you can chunk it to as close to even as possible. Or you can say, oh, I think there's a question in the chat. Let me just look at that. So in the scheduler world, the task is essentially the number of, it'll essentially correspond to the number of MPI tasks. That is the number of processes it's going to launch. The CPUs there actually refers to cores in that in the scheduler option. So when I say CPUs per task there, it's actually cores per task. And then the threads are essentially, so if you launch one process and you say that, okay, I'm going to spawn 8 OpenMP threads, that's what that corresponds to. And what we are trying to do is match that to the number of cores that you asked for, because otherwise you're going to oversubscribe and use. So say I had only asked for 4 threads there and then said, oh, my OMP num thread should be 128. What you want to do is oversubscribe those 4. Or if the scheduler is smart enough, it's probably going to reject the, cause a job failure. But I think most likely what's going to happen is it'll oversubscribe. So you would end up with, 32 tasks on each core, which is not a good thing from a performance standpoint. And this happens quite a bit with hybrid cores. We see this quite a lot with users. Basically, they end up not specifying either, and so the code just looks at the total number of cores and then just uses all 128, for example, and then you do an MPI run with 128. So then what you end up with is 128 processes, each process spawning 128 threads, and which will crash the node because it's going to run out of resources. So you have to kind of make sure that all those combinations are right. So yeah, so going back to the scheduling part, so in the dynamic case, the loop iterations are divided basically dynamically. So and there's a chunk size you can specify. So what that does is, like, when a thread finishes a chunk, it'll just go find another chunk to run. And then guided, it takes it a step further. What it says is, hey, I'm going to keep making the chunk size smaller so that all the cores will always remain busy as much as possible. Like, you don't want to end up like, say one of the chunks is taking longer than the other, and it's possible because if you have a code that is deterministic, determined by, like, say you're doing a chemistry calculation or something, and or a fluid dynamics calculation with chemistry in it. What you could end up with is some locations might be doing a heavier computation than the others, and you may end up with uh, uh, like a unbalanced workload. And then one of the chunks will finish earlier than the others, and the dynamic part helps, but then if the chunk size is large, you're going to still end up with an imbalance at the end. So if you keep reducing the chunk size, then you're essentially doing a Tetris game. You're just filling up slowly. So that's the guided piece. And then runtime is essentially so all these you could set in the code, but you could also set them in the runtime using environment variables, or you could just let the compiler or runtime decide by setting it to auto. So there's all these options. And there is an order of precedence for determining the number of threads. Like if you have some kind of if condition to set the number of threads, or if you set it using the library function or the environment variable, and if you don't do anything, and so in the like when I was doing the hands-on, I was doing it through the scheduler. But say you were locked in through the node with all 128 cores available, and then you don't set the number of threads, it's going to use all 128. So that was a simple hello world kind of example. So let's do a simple OpenMP program that is computing pi. And what we're going to do is find the number of tasks and task IDs, which is what we did in the hello world example. And then the pi is essentially calculated using an integral, and we just set the number of intervals for this interval, and we do the numerical integration, and then the OpenMP part is essentially parallelizing that loop. So let's look at the code. Right, so you have, so we are again including omp.h, and then we have the number of threads and the thread ID, the TID, and the intervals. So we set the intervals to 128,000, and then we are saying we're going to fork the threads here and give them their own copies of the variables. So you have actually the n threads could be shared, but in this case we are just making it private, and we'll just not have an if condition and just call the thing if we want to. But basically here what we are doing is essentially setting the thread ID equals OMP get thread number, and actually I still had the master thing here. Okay. But so now we have a section here that is actually a serial piece. So you would end up with this being calculated n1 equals 1 over intervals, and then another parallel loop to calculate the pi with a reduction operation. So what we are doing here is a parallel for with the private variables I and x, and the shared variables n1, which is the thing we calculated there, and the intervals, which again is common to all of them. And then we are doing a reduction on this variable pi. Okay. And actually I didn't initialize this, but we should technically initialize this, but it'll get initialized to 0, so it should be okay. So you do an integral over all the intervals, and essentially you're finding x based on this interval. So you're doing an integration from, I think, let's say like minus 0.5 to 0.5 is what I'm doing, I think, and it's 4 over 1 plus x square is what you're integrating. So you find the x. So you can see why this should be private, right? Like if we didn't make this private and it was kind of shared, then every thread would clobber this variable here, the x here, because every time it's calculating, it will just overwrite, and then you would end up with the wrong answer. So you made that shared, made that private, and then you're just doing a addition to the existing Pi. This can be shared. It's fine if you because you're just incrementing it. But in this case, actually, it's because we have a reduction, it'll be fine. It's set that way. So it's 4 over 1 plus x squared that we are just adding, and in the end, we are just multiplying it by n1 to get the integral. So that's the simple program, and if you run this, and you can do s bash dash a use 300 pi underscore openmp.sb, you can run this yourself, and you'll see we get the hello from each thread, and then an estimation of the pi. We don't have enough intervals, so it doesn't look that good. So that's the simplest one, where we but there are other things like sections where you can say, hey, these enclosed sections should be divided among the threads, and then you can actually divide them into blocks of work which can be executed once, or you can do a single directive where the code is executed only by one thread, which might be needed in some case. So the example for a sections code is like that. So you have 2 sections here. So technically, if you had 2 threads, this part would run on one, then the other one would run on the other part, and then you would end parallel. So there are also like synchronization constructs. So there's a master, which basically says it's only the master thread running. There's a critical, that region of the code is executed on only one thread at a time. So this is to prevent clobbering a shared variable, for example, if you really need to do that for some reason. You can have a barrier to synchronize all the threads. You can also have a task wait, which basically, if there are child tasks, you can wait for all of them to finish. There's an atomic directive, which again lets you specify a memory location that is updated atomically, so that each thread can writes on its own, so it won't let them all write at the same time. So let's see. So that was some of the work options that you have for splitting up the work and so on. Now let's look at a little bit more complicated example, and this is a 1D heat equation example. And I ran this, I've set this up to run with exactly 3 processes, and if you're wondering why, it was because originally we used to do both the MPI and OpenMP tutorials together, and we actually would show this example with OpenMP in an easy way, and then show how it needs to be split up in the MPI case, because then it gets a little tricky with the boundary conditions, boundary points when you split it up. But anyway, in this case, what we are doing is solving a 1D heat equation, start with an initial condition and just evolve in time. And it's a PDE. What you're doing is discretizing. So when you need the derivative in time, you're saying Tn plus 1 minus Tn divided by delta T is the derivative there. And then you have the second derivative here. And if you're new to numerical methods, you can do a Taylor series expansion and figure out that this actually is accurate to some degree. Like, so here again we are doing now I have a Fortran code here, and we're getting the number of threads from the master and printing it out, and we are saying we'll use exactly 3 threads for this one. We set the initial condition. So now the thing is, remember, it's shared memory programming, so you could just do the full initial condition, or if you're reading in an input, for example, you could read it all into the memory from one task. And then when you do the iteration, now we're saying a parallel do. So this do loop is going to be parallelized with the iGlobal being private, and then the shared variables are the temperature array, the alpha, the delta x, the delta t, and I time. And you can see basically we are just the only thing we are doing is when this global, and again, this is 1 through 9, and it's going to get split by 3. So you're going to do 3 points in each thread. And you're just doing that equation in one shot and just end loop, right? You don't actually need this barrier, but just put it in. And then we write out the solution. So, and if you look at this, it'll iterate through 3 times and then write out the solution. So looking at the runtime library routines, we already saw like the setting of the number of threads and querying the number of threads. You can query the thread identifier. We looked at that also. There are other libraries for basically setting and querying dynamic threads features, querying if you're in a parallel region and at what level. You can have nested parallelism. You can you can actually set and terminate locks, and I didn't get into this, but you can, that tutorial that I talked about has all that. So there are also environment variables. So there's the OMP underscore schedule. So remember I talked about like all the multiple options back in this slide, I think. Let's see, go back here. Out here with the schedule options, the static, dynamic, guided, and runtime, and so on. So that you could set even in the environment variables. So that's the OMP schedule, and then you could also do it with the OMP dynamic true or false. And you have OMP num threads, which we looked at. Then there is the process binding. So you can set OMP proc bind equals true or false. This is another good thing to do so that you don't want your threads wandering around during the run. Because when you have a non-uniform memory access setup, if you move a thread off into a different part of the node, you might end up causing a lot of performance problems. So this binding is very important. And when you do hybrid MPI and MPI and OpenMP, there are flags to deal with this. So there's also this OMP stack size. So this is the size of the stack for the threads. So there was a question, can a core run 2 jobs at an instance? I assume you mean 2 threads. If yes, it can, and which is the problem, because if you end up with 8 threads on the same core, you will basically get 1/8 the performance of what, or even worse, because it's going to cause contention. You're going to have pretty bad performance. So you really need to lay it out so that it runs on different cores, like the threads are on different, mapped to the different cores. And this proc bind lets you do that. And there's also KMP affinity flags or GOMP affinity flags that you can do to explicitly spread things out the way you want them. So the stack size is also important, because if you have a really large memory requirement and you have a stack size that's too small, then the thread, then you'll run out of memory and you'll have problems. So that was kind of a quick overview of like all the pieces that you need. Then there are some performance considerations. So some general OpenMP performance considerations. So try to minimize the use of barriers, critical areas, ordered regions, and locks. And all these things essentially serialize things, right? And you don't want to be doing that. Like if you say you have to do it in this order or in this method, then you might end up with a lot of serialization, and then you will have poor efficiency. You can parallelize at, so you should try to parallelize at a high level. So maximize the work in the parallel regions. Don't, fine grain it and end up with lots of overhead by creating and destroying threads all the time. So that is try to parallelize at a higher level. And then depending on your problem, make sure you use the right loop scheduling approach. The static approach has very low synchronization overhead, but obviously it can become unbalanced. And then the dynamic and guided ones have little higher synchronization overheads, but then they can improve load balancing. So it really depends on your problem. If your problem is quite easy to balance, like for example, your like the PDE solver that I was showing you in the earlier slides, like if that was a 3D PDE solver and you had enough work that you could split across all these uh, threads, and you can easily balance it, right? Because you can say that, oh, you're going to have X number of points on each of these threads, and then you can split that up pretty easily and keep it balanced. But if you have a code that isn't balanced, then you have other issues. And then you should probably go the dynamic time. So the last thing on there is avoid false sharing. And this is what I'm going to talk about in the next few slides. And that's the last piece I need to talk about today. So what is false sharing? So most modern processors have a cache buffer between the slow memory, the RAM, and then the high-speed registers of the CPU, right? And if you look at Expanse, you'll see the architecture of the ROM processor. You'll see there are 8 chiplets on each in each processor, and each of the chiplets has 8 cores, and then the cores are actually 4 of those cores share an L3 cache. So you have a level 3 cache being shared by 4 cores, and then you have a memory bus which is there across all 8 chiplets. So you have another level there. And so there's a cache hierarchy, and then the way, and remember, you have to keep coherency across all of these, the whole node, right? So all 128 cores actually have to be cache coherent. What this means is if you, and there is a size of the cache line. So if you load a cache, if you're trying to write to a particular memory location, and you end up loading a cache line, and say there's an OpenMP code where 2 processors might be writing to different elements of the array, but they end up on the same cache line. Now what happens is one of the cores has loaded this. Actually, both of them are loaded, and then one of them will get invalidated because you have to maintain coherency. So as soon as you write on one of them, the other one, everything will get marked invalid, and then you go all the way out to real memory and come back in, right? So if you're doing this a lot in a loop, like say you have like going back to that PDE solver, you might be doing lots of operations like this, where you might be basically writing to the cache line from multiple threads, to elements in the same cache line from multiple threads, and you'll keep thrashing it. And this on a shared memory node, it will impact your performance a little bit. It really gets bad when you have like virtual shared memory nodes, because then you're going across multiple physical nodes through the network, which can really get bad. But even within a node, it can be an issue. And this will lead to a lot of memory traffic. And on Expanse, you can expect this to be a slightly bigger problem than on Comet, for example, because you have way more cores involved. And what this does is loses. So the reason we have all these caches are because you can pipeline everything and get really fast memory access when you're doing the actual calculations. But if you get false sharing and everything is going back to real RAM, then then you are basically not getting the benefit of the cache, and you're going to get a lot slower performance. And it can be quite drastic depending on what's going on. So this is a code snippet that kind of shows you how easily you can get in this situation, right? So you have, in this case, what we are saying is we are taking a loop where we are updating something, and we have a atomic update also, right? And now you could end up with basically, and if this loop is small enough, you could end up with basically multiple threads updating at the same time on the same cache line. So what are the solutions, right? There are several options. There are compiler directives which will align the variables on cache line boundaries. And some compilers, I think I remember seeing one example where the compiler was smart enough to do that even without asking, and like you do O3 and it actually does it for you. But there are actually directives you can apply. There's also padding of arrays. So essentially what you're doing is making the array bigger than what it needs to be, but pads it with padding so that you end up with array elements that begin on cache line boundaries. Or you can use thread local copies of data, which can be quite a bit of overhead if you're moving a lot of data, but if it's a small amount of data, it might be faster. Because it's still going to have just one read, which is fine. So all these issues only happen on writes, so the reads will be fine. And once it's read into the local copy, then you're not going to trash the other cache line when you're updating. So I think we are right on the hour. So let's see. So in terms of homework, what I said is, okay, first thing is try to run all these examples. I think that was a couple of the tasks that I outlined, is just to run those examples. You can also download this matrix multiplication thing from the Livermore site I was talking about, and run with the different scheduling options and see how useful it is or how you can change. And you can write your own matrix vector multiplication and see if you can improve things. Again, this was a very quick intro. There's a lot of ongoing developments, and there's specifications at the OpenMP site, and Livermore has really good tutorials on all the detailed aspects of this. So that's the link down there. And let me go back and run. Let me share my terminal again, and I'll just run through the examples now. We did the hello world already. So so one thing is, to help you compile, I have a makefile, and I think I need to make sure if I uploaded the makefile. If I didn't, I will upload it. So I wanted to show this because there's a little bit of difference in the compile because of the Fortran piece. So in the makefile, all you're setting the CC to GCC, you can setting the Fortran to GFortran, and the C compiler piece you can recognize. There's the C, the compiler with -f OpenMP. This is just a one on everything, and then -g for debug. If you need to, you can take that out actually. There's a -lm here because I think this uses a square root function, so you need that math library linked in. So that's the reason you have the -lm. And if you look at the heat equation, I had heat underscore openmp.f90, But then I have to add this flag, and the reason is because actually the code is not in the Fortran 90 format. It has the older format, so so you need this fixed form flag. So if you compile it just with G-Fortran, it's going to fail because it will look at the F90 extension and decide that it's a Fortran 90 code and fail because it doesn't have the right form. So that's the dash fixed form here, and then you still have the F OpenMP. So let's compile it. So we'll do a make clean. So remove the old executables and then just do a make. And you can see that it did the Fortran and the GCC. And we have the two files now, heat underscore OpenMP and py underscore OpenMP. So if you look at the py underscore OpenMP.sp, so again, I think we should, and I can make this change and you can make this change yourself also. I'll make this change on the repo also. But basically, let's change this to in task per node equals 1, CPUs per task equals 16. Right, and run this. And I think I'm going to try, hold on a second, let me just make sure I have the right format, but I'm going to add like some binding flags to show you how it looks. Or actually, you know what, I should probably try, let's see. Yeah, so you can do export OMP num bind proc bind equals true. I was trying to see if I can make this verbose. Oh yeah. Okay, so that's, I think that's good. Let me just so you could also do something specific, like let me do this first, and then I'll show you the. So now we can just do sbatch minus a use 300 py underscore openmp.sp. So you have that. It's taking some time. Okay. So yeah, it ran with 16 threads, so that's good. What I was trying to see is if I can get you something that actually does the binding to specific processes. Yeah, so this is the thing. So you can use GOMP underscore CPU underscore affinity if you need to specify particular CPUs. So that's the other option. But anyway, let's not get into it. I'm going to see if I can get the debug info up. So let's see. Yeah. So there's also this debug info. I'm not sure if there's anything that will come out of it, but let me just tell you. So I'm going to do that and run it again. No, we didn't get anything different. I think it's only, yeah, it's not going to do anything. Okay, it's debugging our output if you have some problem, but I think we don't need that now. Okay, so play around with the code. We can hang out for some more time, and if there are problems running the code, we can help you out. It should be fairly straightforward. So maybe stop here and wait for like 10 or 15 minutes while everyone tries out.
Yeah, that sounds great. Thanks, Mahi. Appreciate the effort. Clap, clap, clap. Folks, I went ahead and posted a link to the Lawrence Livermore National Lab tutorial exercises. You can find the different ones on this one chart for MPI, and you can then find the same one for OpenMP. But that'll help you kind of find the Livermore software that we're using in our examples. I should get the OMP one. Any questions for Mahi, or we can sit around like he offered to test and get some direct questions answered? Show of hands, how many of you want to hang around and have a short hackathon? Okay, and if not, then I guess, Mahi, we can release people to call it a weekend.
Sounds good.
Are you guys, is that okay with guys? Everybody, you can start departing and that'll be fine.